Okay, so we just saw an very interesting memory element. So both latches and latches and flip-flop, as you see, are memory element, right? It's not just that latch, which we have seen, was label sensitive, right? Label sensitive means whenever the enable signal was one, it was passing the input without knowing. While in flip-flop, we have got through a technique, we only uh, or your output is only sensitive to the edges, right? Where you are collecting, okay, what is the input which is happening, right? So that is, but both are very much the memory element which you see in the in our processors, right? So now what, once you see that, okay, there are positive edge and negative edge, it simply means that are we registering the data at the positive edge, or are we registering the data at the negative edge? And that we have seen the two ways to implement that also. So this was basically a negative edge, right? If I'm correct, this was a negative edge flip flop, right? So D flip flop, negative edge, and this was our positive edge, right? Where the clock is coming here, D Q. So this is our positive edge flip flop, right? So these are the two D flip flop which we have seen, and now we are going to make an application. So if you are saying this is a memory element, show me where it is used in the memory, right? That is the next thing which you will obviously wonder. And you see that actually this is used very much in the resistors, right? Resistors means, you know what is resistor. If you don't know, let me just briefly show you. So you know that we had the ALU where you were doing this full addition and everything, right? So let's say this is your ALU where you had these A and B bits were there, right? So it's a 8-bit you were doing. So this was your A, this was your B, which was summed into, or in the ALU you had this logic gates, right, which were full adder, whatever, right? Yeah. So this was there, and then you were doing the sum, carry, and those kind of things, right? But this was coming from A0, AB0, those kind of things. So what we see is when we are doing any computation, you would need some kind of registers which are giving this data, right? This register is handling, let's say, A0, A1, A2, like that, A3, A4, A5, A6, like that. So this is the meaning of a register, is basically which is having this kind of uh, you're having this kind of second, let me just, yeah. So we were saying that we were having this kind of registers in the memory where you are saving this bits into the memory, right? And then you take this operand, let's say one read one by one, right, into this, and you are getting let's say S, which is coming and saving in another register, right? Which is your, let's say, S, right? That is how. So then you see that there is a way that these are, which is called as registers, from where you are reading the data and you're writing the data, right? So that is why the whole point of, and we see typically when you study microprocessor, you will hear them again and again, that we are saving this data into the registers, right? So that means that this registers very simply can mean like this, where you are putting, and these are D flip flop, because each flip flop will save the data, right? Whenever your clock is either one, so this is positive edge triggered, right? We are using, so these flip all are positively edge triggered, right? So that means they are collecting data when the triggering is happening, or the clock is going from 1 to 0 to 1, then only it registers data. So let's say when this goes to from 0 to 1, this clock, right, you see the data is registered. Whatever the data is registered serial, you get the data. So let's say this is 4-bit, which is we can say this is Q3, Q2, let's say Q1 and Q0, right? So whatever the data comes, it's called serial in and serial out, because your input is coming serially here, right? It's not coming parallelly. It's serial means that whenever the data, once first clock age comes, you get the data at Q0. Then the next clock age comes, it goes to Q1. So that means there is a shifting which is happening with the resistor. So it's like you have only one entrance to the resistor, right? That's what it means simply. So if these are your S, let's say Q0, Q1, Q2, Q3, you are only feeding in like this, and your output is going like this, right? So there is a serial input which you are getting, and there is a serial output which you are getting, right? So this is just one way, very simple way of designing a resistor, where you are serially entering the data into the resistor, right? And serially output the resistor. So whatever is basically coming first is going to go first, right, out of this, right? Because that's how you are serial in and serial out. Now you can have a register which can be where you are reading the parallelly the data from the register. So basically all the inputs to the register are read at the same time, and you can have the output also. No, so this is not serial, this is parallel out, right? Because you are also outputting the data parallelly, right? So PPO, right? So there you see that you are reading the data. Whenever the data comes, it comes into Q0, right? Similarly, it is not serially connected now, right? So the data does not have to pass through. So that means you are having the data, and the data is available in these states, right, at the same time. So that means if I see it as a resistor, that means you have the data which is coming in each thing, and you have the data available, right, like that. So that is how you would see this resistor behaving. Obviously, when you see this parallel in parallel out, you see there are two other combination. You could have parallel in serial out, right? Or you could have serial in parallel out, right? So there are many different combinations like that one can think of, where these resistors can be made, and depending on the requirement of the processor. Okay, but this is very much made with the D flip flop, which we have seen. Very simple, because it behaves like a 1-bit memory, right? It saves the data wherever, and it reads at the clock edge, right? Where that's where you activate that whatever data you want to save inside these flip flops. Okay, so now very nicely we would now see that, okay, we started with an example where we were talking about designing different kind of logic, right? So that is what the mainly and heart of it. If you want to use let's say for your application, you have a problem where you have a logical expression and you're saying, okay, that is how the state machine should behave, uh, then that is the basic idea which would happen. And a very simple example was which we saw was the penny slot machine, right? Which we saw as a. So you saw very clearly that if I had a penny, right, which I was passing into, uh, unless it goes, so sorry, it goes, let's say like penny one, right? Then there is a penny two which goes, and then only the candy comes out, right? Candy out after penny two. So that means this is kind of following some states, right? So because it is saying that, okay, you are not going to be, so you're not going to be one when you have just the penny one, right? Or the candy is not, because it is, there is some kind of uh, state which is happening, that we are going from one penny to another penny. And let me show you the state diagram how it may look like for this kind of problem, right? Yeah, this kind of thing, right? So this is a one of the example we can see where you have the initial case, right? And from the initial case you are seeing that how it is happening, which is accepting different rupee notes, right? So if you are giving, like I said, that you are initializing here, right, this machine, you're giving 2 rupees. When you give 1 rupee only, then the packet is not dropped, right? So you see, when you give 1 rupee, the packet is not dropped, because you see that unless it has the second rupee coming in, then the candy is dropped, right? So this is what is happening, and there are multiple packet which are dropped here. You see that I could directly give a 2 rupee coin. So that means when I give a 2 rupee coin, then I go from 0 to 1 state. So what, from this diagram, what is important is, this is how typically an algorithm and everything works, right? I'm going from one state to another state, right, using some kind of a state machine, right? Which is what is this, the meaning of the state machine is. So a state machine is which says that I am going to go from this to this state. So these are 0, 1, 2 kind of are states, right? So these are your states in this machine. And you see, in this machine, you are going by inserting some input, and there is a certain output which you are getting, right? That is what, and the input of the output of the states basically depends on the previous input what was there, and also depends on, because you see that this is not only depending on the input, it depends on these two state input, right? These two states are also feeding their input, and then this makes a decision, right? So it's not that directly the whatever I'm putting as an output, as an input I can define, right? So it depends on the previous state, and that is what we have been doing in the sequential circuits. So now one would see that how one would make these states, and very simple examples rather than going to first directly to penny slot machine. Let's do first some examples to understand how does one build circuits around it, right? So just to give you more fundamental understanding of that, basically you are saying that this is the state which I am having, right? And this state is your storage elements, which we have seen as D flip-flops, which are there, right? But the next state, whatever is this is going to, right? The next state is decided by the, not just the input. This is the input, but if it was just the input, then this would not make sense as a state machine, right? This is just a, whatever input is coming, you directly get as an output. But what has changed in this is this current state, right? Which is our qn, which we were talking about. This is your input, right? And then this next state, which is qn plus 1, is defining the, based on the, as a function of your inputs and your qn, right? That is the basic idea about the state machine, is that every output of a state is decided by the combination of, or is a function of the inputs in the output of the previous states, right? That is what is happening in this particular circuit, right? So then you see, if that is what is happening in this particular circuit or in this particular block diagram, how do I practice this, right? Because I want to go building this storage and combinational logic, can you guide me through what is the best way for me to go there? So let's see few examples by which we can do all of that in the next video.